Welcome everybody, this is Mr. Anderson for Statistics, Kellogg Community College, and here we are at the end of the video series with Chapter 11, Section 1, the test for goodness of fit. Now, in the previous video we had talked about chi-square distributions, but there are so many good reasons to have chi-square distributions, and we're going to be looking at one of these three in particular here. A chi-square distribution is really great when you want to test a frequency distribution. And testing a frequency distribution is going like let's say you're a soda company and you make 3 different types of Diet Cola, and you want to test to see if you think the preferences of people will actually match what your guess of what they would choose. So testing a frequency distribution is saying like, well, I think people have no preference. So really, if we have 3 sodas, then each of those should be picked roughly about 33.3% of the time. But using chi-square distributions, we can actually test this today to see if the actual data backs up that claim. Chi-square distributions are also really good to test independence between 2 variables. D-E-N-C-E. Spelling is good. Testing independence between 2 variables. That's to see if like maybe a certain political affiliation would believe in something, and that kind of independence test will see if one thing is actually independent of the other, or are they closely tied. And also, chi-square distributions also test homogeneity of proportions, which is a little bit like number 1 here, but to test to see how much they're the same, to see if an actual item has the same kind of proportion as the actual data. But when we do today's goodness of fit test, we're going to be focusing on number 1 there, because the goodness of fit test tests to see if a frequency distribution fits a specific pattern. So going back to the 3 Cokes, let's say you have maybe a Diet Coke, you got Diet Caffeine-Free Coke, and then you have like Coke Zero. And we're not going to include Cherry Coke Zero here for this simple study here, because let's say that the guess is that, well, maybe Coca-Cola thinks that we're expecting, maybe 33%. Everyone's going to kind of pick these evenly. And then what we're going to do is we're going to look at some observed data and see, how many people pick Diet Coke and caffeine-free Diet Coke and also Coke Zero. And what if we come up with maybe 40 people choosing this and 30 people choosing this and then 30 people choosing this? Are these predictions, are these 100 people, the observed data, is that close enough to the expected data to test to see whether there's a preference or not? So let's go and dive into this a little bit and get some vocabulary. The vocabulary here is going to be for our hypothesis testing that we'll do with chi-square distribution. Now, observed frequencies are obtained by sampling. So when we have samples in the story problems, that's what we're going to be doing. We're going to be obtaining them by the samples. So anything that says that we had 50 people or 70 people or 90 people, that's the sampling we're talking about here. Expected frequencies are calculated by the percentages. So anything that's a percent, or if it's evenly distributed, that's kind of given by an even distribution of percents. So like in the last problem I gave, the 3 diet sodas there, excuse me a second, the 3 diet sodas there, those were calculated by a percent, 33%, 33%, 33%, which means that out of 100 people, roughly 33, 33, and 33 would pick it, with maybe 1 in the other category. Okay, so we've got a 5-step problem just like we do with any kind of hypothesis testing. The first step is always going to be your two to state the null hypothesis and the alternative hypothesis. But what makes these cool hypothesis tests a little different in the null hypothesis and alternative hypothesis is these are all going to be in words. There's not going to be symbols. There's not going to be like mu is equal to 0 and mu is not equal to 0. There's not going to be greater than or less than signs. These are all going to be in words. So the hypothesis and the null hypothesis and the alternative hypothesis will come from the story problem. Step 2 is to find your critical value. And your critical value will always be a right tail test. And the reason why it's going to be right tail is chi-squared is always positive. So there's not going to be a two-tail test. Even though in the previous video we did a confidence intervals. Confidence intervals are different than doing z-tests, t-tests, or in this case, chi-squared tests. So we're going to do a right tail test, and that's going to be on table G, which is in your book or on your little laminated trifold sheet. And it's important to note that the N does not talk about the number of people. The N talks about the categories. So in the last example I gave you with the Coke, the Diet Coke, the Diet Caffeine-Free Coke, and the Coke Zero, all of those are categories, so our N would be equal to 3, which means our degree of freedom would be N minus 1. So our degree of freedom would be 2 in this case. Now, our step 3 is to calculate our chi-squared. Now, to calculate the chi-squared, you're going to add the sum of the differences between the observed and the expected values squared divided by the expected values. Now, this looks a little intimidating. The sum of O minus E squared divided by E. Yeah, but once you actually see a problem done, it won't be so bad, especially if you set things up in a table like I want you to. Now, here's a little asterisk that you might have to kind of keep to your, kind of keep in the back of your mind. The categories must have at least 5 people in them. Must have 5 or more people or data points. If some of you are wondering, like, how come when I was talking about the Diet Cokes, how come I didn't include, like, Diet Lime? And Diet Lime may not have enough data points. If someone says, what's your preference, out of 100 people, maybe only 2 people would say Diet Lime. And since 2 out of 100 isn't enough to have 5, then, well, that's going to be thrown out. Now, as a diet soda fan myself, I'm sorry I left off Diet Coke Zero cherry flavor. That is truly delicious. Come on, Coke, get working on a caffeine-free version of that. All right, now step 4 is to make a decision, and the decision is going to have the picture, and the picture is going to be a skewed right. That's because of the chi-squared distribution, and it's going to be a right tail test, so it's always going to be a distribution that looks kind of like that snail or whale, however you want to see it. And step 5 is to summarize. And the summary is going to have basically you either rejecting the null hypothesis or not rejecting the null hypothesis, and then explaining why using inequalities. So what we have is we have 3 of these hypothesis tests that we're going to do from the book. So let's go take a look here. All right. According to a survey of 100 people, the following results are how they preferred a sport drink flavor. Now, with a alpha of 5%, can we be certain that there's a specific difference for each sport drink flavor? Now, I'm going to adjust my worksheet just a little bit on the fly here so we can see all the steps on the page here. All right. All right, if I could get some even spacing there. Sorry, I'm being a little particular here. All right, got to make everything look nice. Would have helped to do this earlier. Okay, so there we go. Steps 1 through 5. Now, the cherry, strawberry, orange, lime, and grape. Now, these are the observed. These are the observed results. So this is from the data. These are observed. And I like putting the observed on my table first. The first thing you have is your categories, then your observed data, and then we're going to have our expected data. Now the expected data is going to be, because really our null hypothesis is that there is no preference. People who choose sport drinks are just going to grab whatever's in front of them. So the company wants to see if there's really a preference for soft drinks, or the alternative hypothesis being there is a preference. So people do choose one flavor over another. Now this doesn't necessarily tell them, now you can look at this and say cherry, but do these little deviations mean that there is an actual preference, or is it just part of your sampling error? So there's our observed data. Now what we're expecting, if we have 100 people not giving a darn about what kind of flavor they have, then this is going to be 20%, 20%, 20%, 20%, 20%, equaling 100% of the data. Now, since we have 100% of the data, that would be 20 people choosing cherry, 20 people choosing strawberry, 20 people choosing orange, lime, and grape. Now, you can see that there are differences between the two, but are the differences enough to say that there is a preference? So in step 2, what we have to do is we have to set up our critical value. Before we get to the actual calculation of the test in step 3, we're going to look at our categories. So our n is going to be equal to 5 in this case, not 100. This is talking about the number of flavors or categories we have. So our degrees of freedom is 4. Then we're going to take our alpha of 0.05, and we don't need to divide that by 2 since this is a right tail test, and look at our chart. Now we're going to go to table G and scroll all the way to the right from the degrees of freedom 4 until we get to 0.05, and that gives us a 9.488 as our critical value that we need to beat. If we beat 9.488, we'll reject the null hypothesis that there is no preference. So step 3. Now here's the part that got a little bit confusing for some of you. You're wondering, like, I'm not sure how to actually compute this formula where I have to add up the sum of the observed minus the expected unit squared divided by the expected. Well, here's how you would do that to find your chi-squared. You're going to subtract these two numbers. 32 minus 20 is 12. And then you're going to square that and divide that by your expected, which in this case is 20. Then you're going to take 28 divided by 20. 28 divided by 20 is going to be 8, and square that and divide it by 20. So you're going these two numbers subtracted, square it, and divide by your expected value. All right, the next one, 16 minus 20 is negative 4. Be careful, you should square that. And you should square it because you're going to want a positive number here. Remember, on your graphing calculator, if you don't put in parentheses, you will get the wrong answer as a negative 16. My suggestion is that when you type this into your calculator, go 12 squared divided by 20 plus 8 squared divided by 20 plus 4 squared. Drop the negative, 4 squared divided by 20, and that way you won't have to worry about the parentheses. Then this is going to be 14 minus 20, negative 6 squared divided by 20, and 10 minus 20, or negative 10 squared divided by 20. And again, as I said, when you type this into your calculator in one string, 12 squared divided by 20 plus 8 squared divided by 20 plus 4 divided by 20 plus 6 divided by 20 plus 10 divided by 20. This way you won't make a mistake with the negatives there. And I'd like you to try to type that in, pause the video, and you will get the answer. And the answer might surprise you because once in this, it's a whole number. So go ahead, type it in. Okay, the answer is 18. So step 4 is to draw our right tail. And it looks like our critical value was 9.488, and we were all the way at 18. Which means that our step 5 is going to be to reject the null hypothesis. And our null hypothesis was there was no preference. Well, we can honestly say that the variations between the expected value of 20 was enough to say, yeah, we're rejecting the null hypothesis because we have 18, which is our chi-squared, which was much greater than our critical value, which is 9.488. And there we go. There's our first problem. All right, moving on to problems 2, 3, and 4. All right, and I'm going to pause the video here and get my stuff set up. All right, now we're on to the second of 3 problems here. We are going to take a look at the story problem in the book, and you'll notice the story problem has a lot of words in it, and we're going to have to do some setup here to make our life easy. So I'm strongly going to suggest that we make a table. Now our table to the right here is going to be set up with categories first. Then we're going to have our observed data, and then we're going to have our expected data. Now the expected data is going to be the tough one in this case because we're not going to be dealing with 100 people, and we'll see that as we go through this. Other things to note, you're going to want to maybe figure out your alpha, figure out your number of categories, and then figure out your degrees of freedom. All of these will be used in steps 2 and 3. Okay, so according to the Russell Reynolds Association, retired executives who returned to work, there were 38% who were employed by another organization. So I'm going to abbreviate that 38% category. This is employed by another organization, and that's going to be expected. We kind of expect 38% to be employed by another organization. And it looks like 32% will self-employed, so self-employed, we'll put down 32%. There's going to be some small numbers written in here, and you'll see that in just a moment here. And it says freelancing, so we're going to put FL. We got 23% freelancing. Okay, and then we have 7 people who form their own company. So let's put FOC, formed own company, and that's going to be 7%. Now, observed. To see if this was true, they asked 300 retired executives who returned to work to see what they did. 122 were employed by another organization. There were 85 that were self-employed, and there were 76 freelancing, and only 17 just went off to do their own company. Now, this adds up to 300 people. Now, what that means is we need to take our expected values, which are percents, and we're going to need to multiply that by 300. You see, normally we would just take 38, 32, 23, and 7 if that was out of 100. But since this is out of 300 people, I would expect 38% of 300, or 0.38 times 300, to be 114 people. Wait, how did I get that again? Take 300, multiply by 0.38 on your calculator, and that gets you what we're kind of expecting. Pretty close, wasn't it? Now, if I take 300 and multiply by 0.32, I get 96. Pretty close. 23% or 0.23 times 0.23 times 300 is 69 people. Again, pretty close. And 300 times 0.21 or 300 times 0.07, not 0.7 but 0.07 is 21 people. And you will see that all of these 4 numbers add up to 300 people. So you can see that these probably, what's your gut telling you? Is your gut telling you that these are pretty close? Well, that's what the chi-square test is for. Because if they're pretty close or they're close enough, then we can accept the null hypothesis, which is that the percentages are correct. Now this is where the book and I differ a little bit, because if you look at the null hypothesis in the back of the book for some of these problems here, it will state that the null hypothesis is that 38% are unemployed by another organization, 32% were self-employed, 23% were freelancing or consulting, and 7% were owned by their own companies. But understand that's the null hypothesis, is basically saying that the percentages are correct. So our null hypothesis would be also kind of shortened here, that the percentages are not correct. So the distribution does not match. Whoa, could my handwriting be better? The distribution does not match. The percentage. Okay, so step 2. Step 2, we're going to have 4 categories. So our n is going to be equal to 4, and our alpha is 10%, and our degrees of freedom will then be 3. So according to our table G, where we look at an alpha of 0.10 with 3 degrees of freedom, our critical value is positive 6.251. Now what we're going to do is we're going to do our step 3, which is the sum of the observed minus the expected quantity squared divided by the expected value. So we take each of these 4 categories, and luckily we have more than 5 in each category, so this is going to be okay. We take 122 minus 174, or 114, and that gives me 8. square that, and divide it by 114. Then we're going to take our 85, subtract our 96, which gives me negative 11, and square that and divide that by 96. Then we're going to take the 76 and subtract our 69, and then we get 7. We're going to square that, divide it by 69. And then we're going to take our 17, subtract our 21, which gives us negative 4, square that, and then divide it by 21. And again, my hint for you is to go 8 squared divided by 114 plus 11 squared divided by 96 plus 7 squared divided by 69 plus 4 squared divided by 21. This way you won't make any mistakes with the negatives on the calculator if you forget your percentages. And this will give you a decimal. Now I'd like you to pause the video, and I'd like you to try this out and see if you can get the right answer. 3.294. So step 4 is to analyze the results here. Well, it looks like our critical value was going to be at 6.251. 3.294, folks. Not in the critical region. So therefore, our step 5 is to do not reject the null hypothesis, which is great. Do not null hypothesis. Do not reject the null hypothesis, which means that the Russell-Reynolds association is pretty well spot on with those percentages and don't need to revisit it. And we didn't reject the null hypothesis because 3.294 is less than 6.251. All right, now we're going to move to the next part of the worksheet here. I strongly suggest that you, after downloading this worksheet, that you actually try to do problem 3 all by itself, and then just try to see how you did when I go through the problem. All right, here we go. I've formatted this problem so it fits inside the screen here, and now what we're going to do is see how well you did. Now again, if you got stuck right from the very beginning, what I would do is make a table, and the table is going to have categories, CAT, and then it's going to have observed values, OB, and then expected values, EX. Now again, some other things that might be nice to find is to count your number of categories, N, then find your degrees of freedom, and know your alpha. So if you got stuck, pause it here and see how far you can go. Now, in terms of categories, we have, according to firearm statistics, deaths for fewer than 19 years of age are in the following categories. There's accidental deaths, so I'm going to put ACC for accidental. Expected is 74%. Then we have homicide, so I'm going to put that as HOM, and that's going to be 16%. Expected, and then we're going to have suicide, which I'll put SUI, which is expected to be 10%. Now, in a sample, there were 68 accidental deaths, there were 27 homicides, and 5 suicides. With an alpha of 10%, find the percentage and see if it matches. Now, our number of categories is 3, and our degrees of freedom would then be 2. But since we're talking about 100 people, and not 300 people in this time, converting this is pretty easy. 0.74 times 100 is 74, 16% times 100 is 16, and 10% times 100 is 10. So subtracting these two is going to be easy for my step 3. Our null hypothesis is that we have percentages are correct. Yep, just kind of quickly writing that, and it looks like I'm quickly writing it. And our null hypothesis, our alternative hypothesis is that the distribution does not match the percentages. Distribution doesn't match. All right, sorry for the little crammed writing there, but I'm just trying to save some space and get it all on the screen at the same time. There's our alternative and null hypotheses. Now step 2. I'm going to take step 2 here, and I've got my kind of information for my step 2 right there. So I'm going to take a look at my table G, and my critical value when degrees of freedom are 2 and my alpha is 0.10 is going to be 4.605. I need to be bigger than 4.605 to reject the null hypothesis. Step 3, subtract these two numbers, which gives me negative 6. I'm going to square that and divide it by 74. Subtract the next two numbers. 27 minus 16 is 11 squared divided by 16. And then 5 minus 10 is negative 5 squared divided by 10. And what's important about that is, again, when you type this into your calculator, it's probably better to go 6 squared divided by 74, 11 squared divided by 16, plus 5 squared divided by 10 in one string, and type that in, see if you get the right answer. 10.549. In our right tail test, wow, that's a horrible tail. Looks like it really does look like a whale. This is shouldn't go up there at the end there. This is 4.605, and we were, look at that, 10.549. And so whatever sample we got here, man, this is definitely inside the critical region. We are going to reject this baby here. We're going to reject the null hypothesis, blam. And we're going to reject that null hypothesis because 10.549 is huge compared to 4.605. All right, again, if you got any questions, shoot me an email. Thanks for watching the videos.